Hi guys, welcome back to engineeringtalks.com. In the previous video, we saw the introduction and concepts related to Laplace transforms, and we learned how to take the Laplace transform of 1. In this video, we learn how to take the Laplace transforms of all the elementary functions and the properties of Laplace transforms, and we'll solve problems using these properties. So, happy learning. In the previous video, we saw how to take the Laplace transform of 1. In this video, we'll learn how to take the Laplace transforms of other elementary functions. So first, let's consider f of t equal to t. So Laplace of f of t, we all know it's given by integral 0 to infinity e raised to minus st f of t dt. So Laplace of t is given by integral 0 to infinity e raised to minus st t dt. Now, for doing the integration, we'll have to follow this Untitled rule. I stands for inverse, which includes sine inverse x, cos inverse x, etc. L stands for logarithmic, log x functions. A for algebraic, which includes x, x squared plus 1, etc. T stands for trigonometric, sin x, cos x, tan x, etc. E stands for exponential, e raised to x functions. So here we can see we have one exponential function and one algebraic function. So what does Untitled rule state? Untitled rule states that we have to arrange the functions in this order before integrating. So here we have got one exponential function and one algebraic function. So let's place the algebraic function first and then the exponential function, because here algebraic function comes before the exponential function. So integral 0 to infinity t e raised to minus st dt. Now this is of the form integral uv dx, right? So we have a general expression for integral uv dx. That is integral uv dx equal to u into integral v dx minus integral into du, that is differential of the first function, into integral of the second function, the whole dx. So let's do the integration. Laplace of t equal to first function into integral of the second function minus integral of differential of the first function into integral of the second function into dt. Why I put 1 here? This is because d by dt of the first function, that is t, is 1. Now t e raised to minus st by minus s plus 1 by s, that is I have just taken this minus s outside, it becomes 1 by s, integral e raised to minus st dt, because 1 into e raised to minus st is e raised to minus st itself. This is equal to t e raised to minus st by minus s plus 1 by s into e raised to minus st by minus s, which is the integral of e raised to minus st, which is equal to minus 1 by s into t e raised to minus st plus e raised to minus st by s. I just took this minus 1 by s outside. Now we'll apply the limits from 0 to infinity. So when we apply infinity, we'll get these two terms as 0, because e raised to minus infinity is 0. So 0 plus 0 minus, and we'll apply 0. So this term becomes 0 and this term becomes e raised to 0 by s, which is 1 by s. So minus 1 by s into this whole thing is 0 and we have minus 1 by s here. So minus 1 by s into minus 1 by s, will get 1 by s square. So Laplace of t equal to 1 by s square. Now let's find out a generalized expression for t raised to n. Laplace of t raised to n equal to integral 0 to infinity e raised to minus st t raised to n into dt. Now let's put st equal to u. So we'll get t equal to u by s and dt equal to du by s. Now let's see if there is any change in the limits. So when t equal to 0, u is also equal to 0, and when t equal to infinity, u is also equal to infinity. Why we have done this is that we have changed the variable t to u, so we have to change the limits accordingly. After substitution, we get Laplace of t raised to n equal to integral 0 to infinity e raised to minus u into u by s raised to n du by s. which is equal to integral 0 to infinity e raised to minus u. We'll take this u raised to n outside, u raised to n into 1 by s raised to n into 1 by s. So it becomes 1 by s raised to n plus 1 du. Now we'll take this 1 by s raised to n plus 1 outside into integral 0 to infinity e raised to minus u, u raised to n into du. Now we can rewrite this u raised to n as u raised to n plus 1 minus 1, right? Because it's effectively u raised to n only. So 1 by s raised to n plus 1 integral 0 to infinity e raised to minus u, u raised to n plus 1 minus 1 du. Now gamma function, gamma of n is given as integral 0 to infinity e raised to minus x, x raised to n minus 1 into dx. Don't worry, I'll put another video separately on beta and gamma functions. So for time being, you just know that gamma of n is given by this expression. So see, do you find any similarities in these two expressions? Yes, right? In the place of n, we have n plus 1 here. So gamma of n is given by this expression. So gamma of n plus 1 will be given by this expression. So we can substitute this gamma of n plus 1 in the place of this expression. So it becomes Laplace of t raised to n equal to 1 by s raised to n plus 1 integral 0 to infinity e raised to minus u, u raised to n plus 1 minus 1 into du. Here we have n plus 1 in the place of n. So we have 1 by s raised to n plus 1 gamma of n plus 1, which is equal to n factorial by n plus 1. So you should know these formulae. Gamma of n plus 1 is given by n factorial. Gamma of 1 is 1. Gamma of 1 by 2 is root pi. And gamma of n plus 1 is also given by n gamma n. So we can generalize the equation. Laplace of t raised to n equal to n factorial by s raised to n plus 1. Now let's see how to take the Laplace transform of the function e raised to at. Laplace of e raised to at is given by integral 0 to infinity e raised to minus st e raised to at dt. So we can combine these two and write it as integral 0 to infinity e raised to minus s minus a t dt, right? Now we'll take the integral of this function, which is equal to e raised to minus s minus at by minus s minus a, and the limits are from 0 to infinity. Now we'll apply the limits. So before applying the limits, let's take this minus 1 by s minus a outside. So minus 1 by s minus a into e raised to minus infinity minus e raised to 0. This is what we get after applying the limits. So e raised to minus 0 is 0 and e raised to 0 is 1. So minus 1 by s minus a into minus 1 is 1 by s minus a. Similarly, we can find out the Laplace transform of e raised to minus t. Laplace of e raised to minus t equal to integral 0 to infinity e raised to minus st e raised to minus at dt. We can combine these two terms, which is equal to integral 0 to infinity e raised to minus s plus at dt, which is equal to, we'll take the integral e raised to minus s plus at by minus s plus a, and the limits are from 0 to infinity. Now after applying the limits, we'll get the first term e raised to minus infinity and the second term e raised to 0. So minus 1 by s plus a into e raised to minus infinity minus e raised to 0, which gives you minus 1 by s plus a into e raised to minus infinity is 0, we all know, and e raised to 0 is 1. So 0 minus 1 is minus 1. So minus 1 by s plus a into minus 1 is 1 by s plus a. So now we have Laplace of e raised to at is 1 by s minus a, and Laplace of e raised to minus at is 1 by s plus a. How can we forget our friends, sine and cos functions? So let's see how to get the Laplace transforms of sine at and cos at. So first, let's consider sine at. So Laplace of sine at equal to integral 0 to infinity e raised to minus st sine at dt. But we have a general formula for finding out integral e raised to ax sine bx dx. So this is of this format, right? So we can use this general formula. So it states that integral e raised to ax sine bx dx equal to e raised to ax by a square plus b square into a sine bx minus b cos bx. Let's apply this formula. So we'll get integral 0 to infinity e raised to minus st sine at dt equal to, we have minus s in the place of a and a in the place of b here. So we'll substitute accordingly. It becomes e raised to minus st by a square plus a square into minus s sine at minus a cos at within the limits 0 to infinity. Now let's apply the limits. So the first, when we apply infinity, this term becomes e raised to minus infinity by a square plus a square into minus s sine infinity minus a cos infinity minus e raised to 0 by a square plus a square into minus s sine 0 minus a cos 0. We all know e raised to minus infinity is 0. So this whole term becomes 0 minus e raised to 0 is 1. So 1 by a square plus a square into sine 0 is 0 and cos 0 is 1. So minus a into 1 becomes minus a. So minus 1 by a square plus a square into minus a equal to a by a square plus a square. Similarly, we can get the Laplace transform of cos at. Laplace of cos at equal to integral 0 to infinity e raised to minus st cos at dt. But we have a general formula like this. So why to integrate and waste time? So the general formula says integral e raised to ax cos bx dx equal to e raised to ax by a square plus b square into a cos bx plus b sine bx. So here in the place of a we have minus s and in the place of b we have a. So let's substitute. It becomes e raised to minus st by a square plus a square into minus s cos at plus a sine at within the limits 0 to infinity. See, I have put minus s in the place of a in the place of b. See, correct, no? Then it becomes e raised to minus infinity by a square plus a square. This is after applying the limits. Minus s cos infinity plus a sine infinity minus e raised to 0 by a square plus a square into minus s cos 0 plus a sine 0. E raised to minus infinity is 0. This whole term becomes 0. And the next term we have e raised to 0. So e raised to 0 is 1. So 1 by s square plus a square into minus s cos 0. Cos 0 is 1. So minus s plus sine 0 is 0. So this whole term becomes 0 plus 0, which is equal to s by s square plus a square, because minus s into minus 1 is s. So s by s square plus a square. So we have Laplace of sine at equal to a by s square plus a square and Laplace of cos at equal to s by s square plus a square. One of the properties of Laplace transforms is linearity property. So let's see what this property is. If a, b, c are constants and f, g, h are functions of t, then Laplace of a f of t minus b g of t plus c h of t is equal to a Laplace of f of t minus b Laplace of g of t plus c Laplace of h of t. That is, we can split and take the Laplace transforms. Now let's find out the Laplace transforms of the hyperbolic functions cos ht and sin ht. So before finding out the Laplace transforms of these hyperbolic functions, let's see the general formulae of sin ht and cos ht. Sin ht is given by e raised to t minus e raised to minus t by 2 and cos ht is given by e raised to t plus e raised to minus t by 2. Now let's take the Laplace transform. Laplace of cos h at equal to integral 0 to infinity e raised to minus st cos h at dt. But we have cos h at equal to e raised to at plus e raised to minus at by 2, because cos ht is e raised to t plus e raised to minus t by 2. Now we just have to substitute this formula here. That is, Laplace of cos ht equal to Laplace of e raised to at plus e raised to minus at by 2. So that we can avoid this integration and wastage of time. So we can directly take the Laplace transforms of these two functions. Now using the linearity property, we can split and take the Laplace transform. We'll take this 1 by 2 outside and we'll get Laplace of e raised to at plus Laplace of e raised to minus at. So we know the Laplace of e raised to at is 1 by s minus a and Laplace of e raised to minus at is 1 by s plus a. So half into s plus a plus s minus a by s minus a into s plus a is s square minus a square. That is a plus b into a minus b equal to a square minus b square format, which is equal to half into a plus a minus a get cancelled and s plus s is 2s by s square minus a square, which is equal to, we can cancel these two, which is equal to s by s square minus a square. Similarly, we can find out the Laplace transform of sin h at. Sin h at is given by e raised to at minus e raised to minus at by 2. Now let's substitute this value here. That is Laplace of sin h at equal to Laplace of e raised to at minus e raised to minus at by 2. Which gives you half, that is we'll take this half outside, Laplace of e raised to at minus Laplace of e raised to minus 8, which is equal to 1 by 2 into Laplace of e raised to at is 1 by s minus a minus Laplace of e raised to minus 8 is 1 by s plus a, which is equal to 1 by 2 into, we'll take this side and this side. So s plus a minus s minus a by a square minus a square, which is equal to this s and this minus s get cancelled and a plus a becomes 2a by a square minus a square. Now we'll cancel these two, which is equal to a by a square minus a square. So we have found out the Laplace transforms of all the elementary functions. Let's move on to the next property, that is the first shifting property. It states that if Laplace of f of t equal to f of s, then Laplace of e raised to at f of t equal to f of s minus a. Now what is the advantage of using such a property? Because if f of s is known, that is we know the f of s of all the elementary functions now. So what we can do is that if we have to find out the Laplace transform of e raised to at f of t, we don't have to integrate and find out the solution. What we can do is that we already know the Laplace transform of that elementary function. We just have to substitute s minus a in the place of s. So if f of s is known, we can get the solution directly without integrating. So that's an advantage, isn't it? So we get the following results. See, Laplace of e raised to at is 1 by s minus a. We all know that. So Laplace of t raised to n, what was Laplace of t raised to n? N factorial by s raised to n plus 1. So if we have Laplace of e raised to at t raised to n, what we have to do is that we just have to put s minus a instead of n, instead of s. So it becomes n factorial by s minus a raised to n plus 1 factorial. So it is actually the same with s minus a instead of s. Now Laplace of e raised to at sin bt equal to b by s minus a the whole square plus b square. And similarly you can see all these Laplace transforms, we just have put s minus a in the place of s. Rest is same. Now if we have e raised to minus at in the place of e raised to at, what we can do is that we can put s plus a in the place of s. That is, if Laplace of e raised to at f of t is to be found out, then we just have to put s plus a in the place of f of s. So we know Laplace of e raised to at, e raised to minus at equal to 1 by s plus a. So Laplace of e raised to minus at t raised to n is n factorial by s plus a raised to n factorial. Similarly, Laplace of e raised to minus at sin bt equal to b by s plus a the whole square plus b square. Similarly, you just have to substitute s plus a in the place of s. So we can find out the solution in a very less amount of time using this property. Solve some problems based on these properties. So find out the Laplace transform of e raised to i60. We all know e raised to it equal to cos t plus I sin t. So e raised to i60 will be cos t plus I sin 6t. So Laplace of e raised to i60 will be Laplace of cos 60 plus I sin 60. Now using the linearity property, we can split the terms. Laplace of cos 60 plus I Laplace of sine 60, which is equal to cos 80. Laplace of cos 80 is s by s square plus a square. So here a is 6. So we'll get s by s square plus 6 square, that is 36, plus I sine 80, that is Laplace of sine 80 is a by s square plus a square. Here a is 6. So 6 by s square plus 36, which is equal to s plus 6i by s square plus 36. Now, Laplace transform of phi t cube e raised to minus phi t. If we get something like this, what we can do? Here we have a term t raised to 3. We all know Laplace of t raised to n is n factorial by s raised to n plus 1, right? So let's find out the Laplace transform of t cube. It's very easy, just substitute the value of n. Here n is 3. So Laplace of t cube equal to 3 factorial by s raised to 3 plus 1, which is equal to 4. So 3 factorial by s raised to 4, which is equal to, what is 3 factorial? 3 into 2 into 1, which is 6 by s raised to 4. Now 5 t cube will be, Laplace of 5 t cube will be, we just have to multiply this 6 with 5. So 5 into 6 will be 30 by s raised to 4. Now we have to deal with this term e raised to minus 5t. We all know by first shifting theorem, Laplace of e raised to minus at f of t equal to f of s plus a, right? Because e raised to minus 8, if there is e raised to minus at along with the function, we can get the Laplace transform just by substituting that s with s plus a. So here a is 5. So what we can do, Laplace of e raised to minus 5t into 5t cube will be 30. We all know that Laplace of 5t cube is 30 by s raised to 4. So Laplace of e raised to minus 5t into 5t cube will be 30 by, instead of s, we'll put s plus a. Here a is 5. So 30 by s plus 5 raised to 4. There is another property known as change of scale property. It states that if Laplace of f of t equal to f of s, then Laplace of f of at equal to 1 by a f of s by a. Let's see how we got this formula. Laplace of f of at equal to integral 0 to infinity e raised to minus st f of at dt, right? Now let's put this at equal to u. Then t becomes u by a and dt becomes du by a. Since we have changed the variable, let's see if there is any change in the limits. When t equal to 0, u equal to 0. When t equal to infinity, u equal to infinity. So there is no change in the limits. Now let's substitute these. So Laplace of f of at becomes integral 0 to infinity e raised to minus s u by a f of u du by a. Now we'll take this 1 by a outside. Integral 0 to infinity e raised to minus s by a u f of u du. We all know that integral 0 to infinity e raised to minus st f of t dt is f of s. Here in this formula we can see that it is similar to the formula which I said now, but the only difference is that instead of s we have s by a. So we can write f of s by a instead of f of s. So Laplace of f of at becomes 1 by a f of s by a. So guys, I hope you all understood what is taught in today's class. In the next video, we'll solve more problems on this and then get into inverse Laplace transforms. Till then, stay tuned and don't forget to like, share, subscribe and press the bell icon. Thank you.